Hi everyone, welcome to Architecting for Observability in iOS Applications. My name is Sergey Misko. I'm iOS team lead with more than 8 years of experience. Today I will briefly tell you about observability in mobile applications, and then we'll tell you what you can do in your iOS applications to make implementation of observability easier. How do we ensure that our application is stable and functioning properly? We test it. More often, this is done by the QA team using various test cases, test environments, and specific devices. But such checks are inherently synthetic and don't always reflect the real-world scenario. In reality, things are much more complex, and observability can help organize real-time testing. Observability is a term that originated from the fields of engineering and system analysis. In the context of software development and especially mobile applications, observability can be described as the ability of a system to provide information about its internal state and operation. Simply put, it's a property of the system, like trustability or security. We need to design the system in such a way that it benefits from observability, meaning the system itself reports its state and provides details in case of incidents. It's important to understand that traces, metrics, and logs by themselves are not observability. These are just tools that can help achieve this property. True observability is built upon aggregating all collected information in one place, where it can be analyzed, visualized through graphs or dashboards, and where alerts can be set up to trigger when the number of incidents increases. Good observability allows a team not to quickly respond to emerging issues, but also to anticipate them. This means the system itself hints at what is wrong and helps identify the cause immediately. Imagine not having to figure out where exactly an error occurred and what caused it. The system directly informs you. Observability is a key tool for creating reliable and resilient mobile applications. It minimizes the time needed to detect and fix issues, thereby improving the overall user experience. You can learn about the problem from users when they start complaining, but observability helps solve two crucial aspects. You learn about the problem before it becomes critical, and you have complete information and can immediately start resolving the issue without needing to gather data from various sources. To summarize, with good observability in your project, you don't just find out that a problem occurred, but you immediately get all the necessary information to solve it. The system fully reports its state and the causes of any issues, allowing you to take action promptly. However, it's important to remember that observability does not replace classic testing. Synthetic checks are still necessary. The topic of observability is widely known among backend developers and DevOps engineers. However, in mobile application development, this topic is often overlooked. Even though many teams and projects have already made steps towards observability, perhaps even without realizing it. Let's imagine a hypothetical project, an iOS application. The team that developed it didn't integrate analytics, logging, Crashlytics, or other monitoring tools. It's just a project with a set of features. After releasing a new version, users began to report that app is not working. It crashes by itself. Or when I open the second screen, the app crashes. These reviews indicate that something went wrong, but don't provide clarity on what exactly and why. The team tried to reproduce the problem but found nothing unusual. The app seemed to work fine in their environment. However, users continued to complain, suggesting a possible crash. But since the team couldn't reproduce it, they were left to work blindly, release new version and hope it works. As example, this situation could have been easily solved if the app had been set up with Crashlytics to catch crashes and send information about them. In the world of iOS development, Apple already provides such functionality out of the box, but with certain limitations. For greater flexibility, developers often turn to third-party services like Firebase Crashlytics. Today, collecting crash information has become a standard practice that allows teams to learn about issues before a user starts complaining in large numbers, while also providing data on the causes of these issues, such as stack traces and technical information about the device. By working with Crashlytics, teams are already taking that step toward observability. However, crashes are far from the only problem that can lead to user complaints or worse, cause a drop in key metrics and revenue. The more complex a system becomes, the more dependent parameters it includes, the more diverse the devices and OS version it supports, the less transparent it becomes in understanding how the app behaves in real-world conditions. For example, if a project uses feature flags to manage the availability of features and the configuration system doesn't validate changes, so a product manager or business analyst could accidentally make an error, such as miscast the data format or skip an important field. This could result in users not receiving certain functionalities, even though the server and Crashlytics don't register any issues. Moreover, given the complexity of modern systems, it's impossible to test and simulate every possible usage scenario. For example, you might release several new features simultaneously. Everything works fine in the test environment, so you release the update. However, on real devices, under certain conditions, such as specific phone model, iOS version, internal app settings, and other, many users might experience issues. For instance, the app may take a long time to load, or critical flows like registration may start to fail, and you will see nothing on Crashlytics because there are no crashes. So, just like with crashes, you need to build metrics for other aspects of the app's performance and stability. To determine where to start building metrics, I suggest focusing on three key aspects. First is important user stories. For example, registration, login, payment processing, sending messages, generating resources, search results, and etc. It's important to consider not only whether these flows are functioning, but also how well they're performing. As example, how quickly payments are processed or how quickly messages are sent. Next, paths, flows, features, stories that depend heavily on dynamic changing arguments. As example, feature flags, country codes, and location. And flows, features, and stories dependent on external systems. This could be a third-party APIs or services, as well as internal systems developed by another team within your company. It's not guaranteed that these teams consider potential issues that might affect your specific app, as opposed to the entire system. This part of the talk provides a general idea of what observability can look like in mobile application. In the next section, we will explore architectural solutions of the iOS side that can help you implement observability in your app. I recommend exploring articles, talks, and other materials, not limiting yourself to mobile development. The experience and approaches of DevOps and backend developers can be very valuable. Achieving good observability means not only knowing that a problem has occurred in your system, but also providing details that explaining what exactly went wrong. One way to gather such information is by using logs. While metrics provide a general overview of the system state, logs collect detailed information about what happened on the user device, what actions they took, and what might have caused the problem. It's crucial to remember that any tools for achieving observability adds overhead, and logs are like one of the heaviest tools. So let's see how we can collect and deliver logs. First of all, we can use live or on light mode. In this mode, logs are sent immediately after they are recorded in the application in real time. This is often used in the backend development, but may not be the best option for mobile applications, as you'll receive logs even everything is working fine for the user. This creates a large amount of unnecessary data, which can be difficult to process and store. However, it's possible to configure the system so that logs are only sent when a specific flag is activated in the app or when a trigger event occurs. It's essential to test this logic to avoid errors that could lead to either losing all logs or being overwhelmed with unnecessary data. Next is on demand. There are two sub-approaches here. First, automatic, where through a login flag which user receives upon entering the app, indicating that logs should be sent, or via a push notification that also prompts the app to send logs. Or we can do it manually. The user can select an option in the menu to send logs upon your request. And the last one is triggered. Logs can be automatically sent when a specific event occurs in the application, such as crash or critical error. And how we can collect our logs? First of all, we can make continuous collection. Logs are recorded continuously, but it's important to consider next things. Avoid recording too many logs at once to prevent overloading the disk with read-write operations. Implement log file rotation to prevent them from becoming too large. For example, you can set a file size limit of 20 megabytes, after which all data is either cleared or overwritten. And carefully manage login levels. Debug logs, which are useful for testing and beta versions, should not be included in continuous login for release versions. On-demand log collection can be activated manually by the user through settings or automatically via a login flag and push notification. And triggered. Just like with delivery, a trigger event can start the log recording process. The last two approaches are quite convenient, especially when dealing with specific issues encountered by individual users. However, these methods have drawbacks. For example, you might miss the initial problem because the logs will only start recording after you've identified the issue and asked the user to enable the log collection. In such cases, the root cause of the problem may be lost. But also, you can implement a combination of logging approaches. For example, logging at the error, warning, and critical levels can happen continuously, while more detailed logs, info, and notice can be enabled when a trigger occurs upon user request or via a login flag. This approach helps maintain a balance between having detailed information and optimizing the costs of storing and processing logs. How we can write logs in iOS devices? First of all, we can use Apple's OS log. Apple offers this powerful tool that includes many optimizations for fast performance, with deep integration into the operation system and support for privacy tools. However, for our purposes, it may be inconvenient. These logs can be difficult to access. There are three ways. First, we can connect the phone to a computer and view the console, which is not so comfortable for the users. Second, we can collect a system diagnostic of the entire device. But it takes up to 15 minutes to collect and results in more than 200 megabytes archive. And also, we can get the logs programmatically from the app, but there is a drawback. You can only get logs from the current process. This means you can't retrieve logs from extensions or from previous launches of the application. So I'm suggesting you not to continue with the OS log. So another approach is to write logs to a text file. You can start by using an existing framework, for example SwiftBeaver, which writes logs to a file. Later, when you become more familiar with logging and understand your needs, you can modify it, since it's open source, or implement your own solution, as it's quite simple, just write into a file. Or you can write logs in Firebase Crashlytics. By default, Firebase Crashlytics is used to catch crashes and send stack traces and device information. But you can also log additional data, such as information about subscriptions or user roles. This allows you to more accurately identify the context in which the error occurred and potentially find a solution more quickly. You can also write logs to Firebase Crashlytics, which will be sent along with the crash report. You can also send a non-fatal event that includes all the information. However, since Firebase is a free service, it has limitations, such as data sampling, so not all events are saved, and a limited number of log times before an error occurs. Additionally, you cannot run custom SQL queries to retrieve the specific data you need. Therefore, it's not advisable to rely on free services for too long. You should consider more specialized solutions or build your own. However, Firebase Crashlytics can be sufficient for a start. And I want to give you a few general advices for writing logs to a text file. Define a login policy and use login levels appropriately. It's important to consider how these levels will be used and to monitor the amount of logging during code review. This helps prevent situations where too many logs are recorded at once, which can negatively impact the system and the disk. This task is as crucial as controlling the number of network requests or database queries as the application functionality grows. To prevent logs from being included in release builds and causing unnecessary overhead, you can use preprocessor directives like if-defined. Instead of adding if-defined to every login statement, you can optimize the login function itself. If defined directive is enabled, the login code is executed. If not, the function remains empty. For example, this can be done for the debug level logs. This allows Swift compiler to exclude unnecessary calls in the release build, ensuring high performance. And also use autoclosure. In your login functions, specify the argument that passes the log text as autoclosure. This allows you to delay the evaluation of the argument until it's actually needed. If logging of this level is not enabled, the evaluation of debug descriptions will not occur, reducing the system load. While logs indeed provide a lot of useful information, they can be cumbersome due to their peak volume. Therefore, it's important to consider various optimizations. One such approach is to transmit a detailed state of the application instead of full logs. For example, you could send information about which screens the user navigated through, which API requests were made, what settings were configured, and which key business logic flags were set. Let's consider an example of notification service extension. This extension is triggered when a push notification with a specific flag is received. The system then allows us to modify the content of the notification or even generate multiple notifications instead of one. For our business logic, we might take an HTTP request to our API, query a database, save changes, and much more. However, there is a catch. iOS strictly enforces a 24 MB RAM limit for your extension. If you exceeded this limit, the system will immediately terminate your process without any notification. This means the user won't even know that something went wrong, and no events will be logged in your metrics or crash reporting tools. Knowing that the notification service extension is not fully executing is not enough. It's crucial to know at which stage it fails. So we need to track every step of our process, send some kind of result, and ensure that we don't introduce so much overhead that we ourselves become the cause of exceeding the RAM limit. A simple solution is to use an option set, where each bit represents a specific step in the notification service extension process, and one of these bits indicates that the extension has reached its logical conclusion. If we complete a step, we set the corresponding bit to 1. Each time a change occurs, we should save the option set value to disk. Then on the next launch, we can check the value of the last option set to determine whether all necessary steps were completed and if the process reached its end. If we detect any deviation, we can send a metric. This way you can see if your extension frequently encountered errors or is being terminated by the system due to exceeding the run limit. Thus, instead of large volume of logs, you can focus on capturing specific key events and states, which will not only save resources, but also simplify data analysis. With a well-structured architecture in your application, implementing various metrics becomes much easier. Honestly, there is nothing fundamentally new here. It's important to follow established patterns, and don't forget about the solid principles, especially the single responsibility principle. This will help you better monitor the areas in your code that require attention. For example, let's consider how the coordinator pattern can help us. Using the coordinator pattern for navigation allows us to clearly track the user path through the screens and their current state. Each coordinator calls another, and thus you can easily compile all the information about the user's journey into an optimized string, such as registration, intercode, main screen, more screen settings. Or you can even reduce it into something like this, where each designation represents a specific screen or transition. This data can be easily decoded for analysis. You can also use the coordinator pattern to determine the last screen the user was on before closing the app. You can send such a metric based on the hypothesis that if many users close the app while on a specific screen, there is likely something wrong with this screen, or users are unable to exit the screen, prompting them to restart the app. To achieve this, you simply need to identify the active coordinator in the application will terminate method of the app delegate, ask it for the current screen, log this information, and send it to analytics on the next app launch. With the coordinator pattern, this can be done quite easily while keeping your code clean. We can also build an app start time metric based on how quickly the user gains access to the app after launching it. Again, using coordinator, you can measure the time difference from app startup to when the app reaches a specific state according to your business logic. Or you can monitor how quickly users complete important flows in your application, such as payments. If users suddenly start taking significantly longer to complete a payment flow, you will notice it right away. Additionally, you can work with the API layer by recording which requests were made during app startup or during its operation. This data can be useful for understanding the sequence of user actions and identify potential issues, as well as spotting bottlenecks during app startup. This will be easy to implement if you clearly defined your API and network entities. Another interesting and useful metric I recommend is Annoyed Tap. This metric tracks situations where the user repeatedly taps on the same UI element, which may indicate frustration due to something not working properly. Such a metric will be easy to implement if you have a clearly defined entity that handles the business logic of the screen, such as interactor, controller, or view model. That's it for today. Thank you for your attention and interest in the topic. I hope you get a better understanding of how to start implement observability in your iOS own projects. Best of luck with your future developments, and thank you once again for being here today.